definition of Fourier transform and the convergence of Fourier transform, and also this Fourier transform for periodic function this time. Okay, and today we are going to talk about properties of Fourier transform. It's going to be similar to the property of of the Fourier series, so some of them we'll go over pretty quickly. Okay, so we start with the linearity, and as usual, Fourier transform is linear. So if you have x of t Fourier transform to some big X of j omega, y of t Fourier transform to big Y of j omega, then ax plus by will Fourier transform to a big X plus b big Y. Okay, so this is the usual linearity. And just like Fourier series, we can have this time shift property. Okay, so if we time shift our signal x, so we have x over t minus t0, then you will Fourier transform to similar to big X of j omega. You get this extra factor of e to the minus j omega t0. Okay, and this can be gotten pretty quickly from this inverse Fourier transform equation. So replace t with t minus t0, then you get extra minus t0 here, then you see that you get extra e to the minus j omega t0 with your with your big X. Okay, and so that's time shift. And with linearity and time shift, we see that we can do calculation for some of the Fourier transform easily. Say if you want to do Fourier transform with this weird shape, and if you want to do straight up integral, will be kind of hard. But then you can recognize this as a summation of two block signal plus and with another time shift. Okay, so x over t will be this x1 of t plus x2 of t, and so 1/2 x1 of t. So for this small part, and plus x of t for this other base part, and then time shift by 2.5 because there was those two signals position and the middle being 0, and this signal has this middle being 2.5. Okay, and for those block signal, we know that we have calculated its Fourier transform is the sinc function. So this is sine 2 sine omega t1 over omega, and so t1 for this one is 1 over 2, and t1 for this one is 3 over 2. So we have a big x1 and a big x2, and then as we say, we have 1 over 2 x1, so 1 over 2 cancel with these 2 plus x2, so we have x2 here, and time shift by 2.5, so you should have e to the minus j omega 2.5. So this is e minus j omega times 5 over 2. Okay. And yeah, so we see that time shift and time shift property and linearity can let us piece together Fourier transform for complicated signal from easier signals. Okay, and then the next part is conjugation and conjugate symmetry. We've talked about this quite a bit when we talk about the Fourier series. So, and I think our presentation is actually simpler. So. We will go pretty quickly, ignoring a lot of the text here. Okay, and so first is what happens when you conjugate your signal. So we have x of t Fourier transform to big X of j omega. Then if we take a conjugation on x, so you have a star of t here. Then what happens is you get a conjugation on your big X, and also you need to add a minus sign on your omega. So this is similar to this conjugation symmetry for AK. Remember we had this x star of t will Fourier transform to a star of minus k. And I think the proof is also very similar. So you take this Fourier transform equation and do conjugation on both sides. And so one side you have x star x star of j omega, and on the other side you conjugate everything. So you see the x. This small x get a conjugation, and also the other complex number is e to the minus j omega t. So you get a minus sign on your e to the minus j omega t. Okay, and then you want your e to the minus j omega t back, so you add a minus sign on omega from both sides. So you see your x star of minus j omega is the Fourier transform of x star of t. Okay. And yeah, so the derivation is very similar. I think you can also do that with this derivation. You take a star on both sides, okay? And star on both sides and put a minus sign in front of your omega, okay? And anyway, so this is a proof, and just like before, when you restrict x to be real, that means x star equal to x, then small x star need to equal to small x, then big x star manager omega should equal to big X over omega. Okay, and you move things around a little bit, so you have x of minus big X of manager omega equal to big X star of omega. This is similar to this equation we had before. Okay. Okay, so we see that with x of t real, then on the frequency domain we have that big X of j omega equal to x star of j omega, and we have an example. So we have this real signal, this is exponential decay starting from zero signal, and its Fourier transform was this 1 over a plus j omega. Then we see that we take a negative sign on its omega, and that's equal to, you take the complex conjugation with this thing, that's adding a negative sign in front of this j. Okay, so this check out. Okay, and I guess then now we want to combine with the time reversal symmetry. So we go over back to a bit review on from chapter 3. So chapter 3 we have those two symmetry, right? So we have the time reversal symmetry says that you get the minus sign on your t, you get the minus sign on your k. So your xt is even, and your ak is even, xt is odd, ak is odd, and they combine with this real analysis, real and imaginary analysis. So you see that if your signal is real and even, then your ak will also be real and even. And let's go over this this idea quickly once. So it says that if xt of real even, and we know that so from even we have ak equal to a minus k, and from real we have a minus k equal to ak star. So from ak equal to ak star we have that ak is real. Okay, and similarly if x of t is real and odd, then ak will be imaginary and odd, etc. Okay, and from those we get the decomposition of real x of t. We see that if x of t is real, then the even part will correspond to this real part of ak, and so this part will actually be real and even, and then the odd part will correspond to imaginary part of ak, and it will be imaginary and odd. Okay, and here we are going to do very similar thing to those two slides. Okay, so we start with our real x of t, and then and yeah, so just like this slide, now we decompose our x over big X over j omega correspond to our real x of t to the real part and imaginary part, and we see that if your x of t is real, then because we have this thing, then the real part will be even. Okay, because we have x of manager omega equal to x star of j omega. Okay, and okay, so we get manager omega on both sides. Then we see that how do I say? Okay, and so we have the manager omega, then both sides has become manager omega, and but when we at the start, then the real part is still the real part, but when we start, the imaginary part get the minus sign. Okay, and so we see the real part is even and the imaginary part is odd, as we derived before. So from here we have this real part is even and the imaginary part is odd. Okay, and so this is a different derivation. So I guess this derivation is we got without doing the analysis. Okay, and then we have a bit of extra thing. So we can get this even odd property also on the polar form of big X. Okay, so we have big X over j omega equal to its amplitude and its angle. Okay, and then we see that, so we do similar things. So this thing we can have this thing with minus sign on omega is this thing. So is amplitude with minus omega and angle with minus omega, and equal to this thing with complex conjugation. So the amplitude doesn't change, but the angle get the minus sign. Okay, so you compare those things, they should be equal. They are equal, then you see that the amplitude part stay the same with when you add the minus sign omega. So the amplitude part is even, and the angle part gets this h1 minus sign. So the angle part or the phase part is odd. Okay, so this is what we know for real signal. Okay, and then just as before, we know that. Yeah, so here we have different derivation, but I guess it's easier to go from bottom to top. So it's very easy to derive that x of t also, when you do time reversal, the Fourier transform has a similar property as the Fourier series. So you get a minus sign on t, you also get a minus sign on omega. And I guess here is kind of a derivation. So from this equation, from the Fourier transform equation, you get a minus sign on your omega, and then you can do the sorry, this is for even. Okay, and but anyway, you can do calculation similar to this, and you see that when you get time reversal, then you get this frequency reversal. And from here, you can get that if x of t is even, big x of j omega is even, and x of t is odd, then big x of j omega is also odd. Okay, and okay, so now we have time reversal, and then we can have this even odd, even odd, and real imaginary analysis. Okay, and I guess it's easier to see. Okay, so I guess let's go to one of the example. So if we have real and even, so this is similar to what we do for AK. And I should highlight this real and even here. Okay, so this is one of the examples. So if we are real and even, and we will have I guess here we go to kind of different directions. So we start with the big S of j omega, then from even, then so okay, so this is the opposite direction of what we had before. Okay, so for real and even, we have I should put. Okay, let's see. Okay, so for real and even, we have this thing, right? So we have AK equal to A minus K equal to AK star. And here it's similar, so but we swap left and right. So we have a big X over j omega equal to big X or minus j omega equal to big X star. Okay, and so as before, so big X j omega equal to big X minus j omega, this is from even. Then big X minus j omega equal to x star of j omega, this is from real, and from this equal to this, big X star equal to big X, then we know big X is also real. Okay. Okay, and yeah, so we know that if small x of t is real and even, then big X is also real and even. Okay, and then we can combine all four possibilities, right? And on triple 3, we only had those two, so we also we only have what happened when x of t is real. So x of t is real and even, and big X of j omega is real and even, and x of t is real and odd, then big X of j omega is imaginary odd. And you can do a bit even more. You can also think about what will happen if x of t is purely imaginary. And from the conjugation symmetry, you see that if x of t is purely imaginary, then big X of j omega needs to satisfy this big X of j omega equal to h1 minus psi. So minus psi, you big X of j omega, you have a kind of 3 minus psi here, so you have a minus, and you have a star on your x, and also minus j omega. Okay, this h1 minus psi is from x over t being imaginary. Okay, so those two equations all comes from our conjugation symmetry, which says that, let's write the conjugation symmetry once again. Says x star of t will Fourier transform to big X dot of minus j omega. Okay, and yeah, so this extra minus sign is gotten from when x is purely imaginary, you do a conjugation on x, you get the extra minus sign. Okay, and yeah, so from time reversal symmetry you have those two results, and from conjugation symmetry you have those two results, and then you have 2 times 2, you have 4 different results here. Okay, and so the real result, once again, the real result are just which is 42. Okay, those two results, real and even, real and even, real and odd, and imaginary and odd. And then we can also have x of t being imaginary and even. Then big X of j omega is imaginary and even, and x of t is imaginary and odd. Then big X of j omega is real and odd. Okay, and yeah, so the logic are very similar to this logic here, and you can do a derivation to basically combine one of those two and one of those two, and you can do a derivation here. Okay, and yeah, then finally, then we have this decomposition of a real function just like before. So we decompose the real function into the, I guess as a review, let's go through the logic once again. So we have now a real function, we decompose into the even part and other part, and we do Fourier transform, and you can easily show that the even part will Fourier transform to, so here is the bilinearity, and so you Fourier transform this thing is Fourier transform of even part plus Fourier transform of odd part. Okay, and okay, so the logic here is that by the analysis we had before, then we know this is real and even, this is real and odd, and so this should be real and even, and it should be imaginary and odd. Okay, so just from those things. Okay, and from there, then yeah, and so we know this thing is purely real and this thing is purely imaginary, and so yeah, and yeah, so this this part is so this part is the real part of this thing, and this part is the imaginary part of this thing. Okay, so we know that the even part of x will Fourier transform to the real part of big X, and the other part of x will Fourier transform to the imaginary part of big X. Okay. Yeah, so that's the result we get, and we have one more picture that says how this thing goes. So we have so any function x of t. So here we have that any function x of t has even part and odd part, and big X of j omega corresponding to the even part of big X and the odd part of big X. Okay, and then we can further decompose those into the real and the imaginary part of even, and the real and the imaginary part of odd. Okay, and and then we can have a correspondence here, just from the result up here. So this real even will correspond to the real part of even, and the imaginary part of even will correspond to the imaginary part of even, and then the real part of odd will correspond to this imaginary part of odd, and the imaginary part of odd will correspond to the real part of odd. And finally, we say x of t is real, then we only pick out the real part, pick out the real part of x of